You're tuned in for another deep dive, and today we're getting into some really fascinating stuff coming out of Q Research.
Yeah, they've been doing some pretty serious work on testing and refining AI models.
Exactly, and we've got the inside track on their whole process,
Uh-huh.
our mission in this dive,
Hmm.
really trying to grasp how AI performance is improved through this sort of back and forth, this testing and tweaking.
It's like seeing the nuts and bolts,
Yeah.
how they actually make these AI systems more effective.
Right. And the core problem they're tackling is how well an AI can tell the difference between data it's seen before,
Mhm.
defined data.
And completely new stuff, the undefined data.
Yeah. Their go-to example is something we all deal with, spam email.
Oh, yeah.
How good is an AI at spotting the usual junk versus something totally new that, might even be more dangerous?
That's spot on. It's really about that core AI challenge of generalization, right? Dealing with the unexpected.
Hmm.
And the spam thing works because it's always changing. New spam tricks pop up constantly. So the AI has to be good at recognizing both the familiar stuff and the brand new threats. This coup research gives us a really detailed look at their strategies.
Okay, so let's unpack their first approach. They talk about Model A.
Uh-huh.
It started with, 29 classes or categories, and later they bumped that up to 47.
Right. Quite an increase later on.
Now, with that initial smaller set, Model A showed high recall and accuracy, but its precision, that was lower.
Okay, yeah. So high recall means it's catching most of the actual spam, right? Grabbing the real junk.
Exactly. But precision is about how accurate those flags are, avoiding the false alarms.
Got it. So Model A was good at catching spam generally, but maybe flag some good emails too.
That's it. Their numbers showed they correctly ID'd 8 out of 10 actual spam emails, so 80% recall. Pretty good.
Okay, 80%. Not bad.
But they also flagged 7 good emails as spam. That brings the precision down to about, 53%?
Oof, yeah, 53%. So the 91% accuracy sounds good at first.
Right.
But those false positives, flagging good emails, that can be a real pain for users. You might miss something important.
Totally. And that kind of sets the stage for Model B, which isn't fully laid out right at the start, but
They hint at the need for it.
yeah, the research highlights this need for a model with high precision, something to accurately check the samples that Model A flagged.
Ah, okay. So a two-step process.
Looks like it. The strategy seems to be use Model A, with its high recall, to cast a wide net first. Catch anything potentially undefined.
Okay, get everything suspicious in one bucket.
Then have Model B, the different type of model focused on high precision, really examine that filtered set and make the final, more accurate call.
That's actually quite smart, this intentional division of labor.
Yeah.
Model A is the initial sweep, making sure nothing potentially threatening slips through, even if it means being a bit overzealous.
Right, erring on the side of caution, even with some innocent emails.
And then Model B comes in, the meticulous analyst, carefully sorting through what A flagged to weed out those false alarms.
Okay, let's get into the core principles. What really sets Model A and Model B apart? They have this really useful table.
Oh, yeah, the comparison table.
Uh-huh.
Helpful.
So Model A, high recall, its job.
Mm.
That big initial filtering, 4 stars for recall, but just 1 for precision.
Ouch. 1-star precision.
Yeah, but the plus side, simple structure, so it's fast, easy on resources.
Okay, efficient.
Right.
But the downside, as we said.
More false positives. Yep.
Right.
Now, Model B, basically the opposite. High precision, acts as that precise verification, the narrow sieve.
So low recall, high precision.
2 stars recall, but 4 stars precision. So yeah, its strength is picking up subtle patterns, detailed classification.
But the trade-off there is.
False negatives. It might miss some actual threats because it's being so careful.
Right, right. That table really nails that fundamental balancing act in classification.
Cool.
You can make a model super sensitive, catch everything high recall, but then it cries wolf a lot, low precision.
Uh-huh.
Or it's super selective, only flags things. It's really sure about high precision, but then it might miss some real cases. Low recall.
And which one you want really depends on the job.
Absolutely. For spam, maybe missing an important email because it was wrongly flagged is worse than letting a bit of spam through. Maybe.
Yeah, that makes sense.
Yeah.
And this difference, this focus, is tied to the number of categories they're trained on and their decision boundaries.
Ah, okay. Explain that a bit.
Well, they say set A, fewer classes, simpler model like our initial Model A, has a wider decision boundary.
Wider boundary, like drawing broader lines between categories.
Kind of. More forgiving lines.
Yeah.
This makes it less likely to misclassify stuff it has seen
Okay.
and better at identifying what's truly undefined
Mm-hmm.
because it's not trying to force it into a narrow box.
Got it. And set B. More classes, more complex model.
Yep, leaning towards our Model B idea. Tighter decision boundary, like very precise lines.
So better at telling known things apart.
Right, but more likely to misclassify something new
Mm-hmm.
and less likely to just say, I don't know, or undefined.
Huh. That's quite insightful. How the complexity, just driven by the number of categories, shapes its whole behavior.
Yeah.
A simpler model, fewer boxes, is more likely to say, this doesn't quite fit. More undefined.
Whereas a complex one, loads of fine-grained categories, might try to shoehorn everything into some box.
Leading to more misclassifications, fewer genuinely uncertain flags.
And this brings us to some of the math they mention. Under the hood,
All right, let's see it.
they use C for the number of learned classes, then P misclass X, probability of misclassifying sample X,
Okay. P misclass,
and pundefined X, probability of classifying X as undefined.
P undefined. Got it.
Their key idea or assumption is that as you increase C, the number of classes, the feature distance between those learned classes gets smaller. They even write it as D is proportional to 1 over C.
Okay, so DO1C. Makes sense. Like sorting colors, a few basic ones, easy to keep separate,
Yeah.
hundreds of similar shades, the lines blur. You're way more likely to put one in the wrong pile.
Exactly. That's the idea with the AI here.
Okay.
Because those classes get more similar, the chance the AI gets overconfident about assigning sample X to class Y,
Well played.
that actually goes up.
Interesting. More similar classes lead to more confidence, even if it's wrong.
Seems like it.
Yeah.
And this overconfidence plus having more classes to potentially misclassify into means a higher chance of mistakes.
Ah.
They give us PIM class X is proportional to C times pi confident.
P misclass COO pi confident. So, more categories and stronger, possibly wrong, belief equals more errors. Concise.
Yeah, it's a neat way to put it.
And it really backs up their practical findings, right? About Model A versus the later set B with more classes. It's not just a feeling, there's a mathematical reason.
Definitely. Now let's look at how they actually tested these models. They talk about 2 key principles, reproducibility and diversity.
Okay, important evaluation concepts. Reproducibility first.
Yeah, reproducibility here is about checking for data-specific quirks or biases.
How do they do that?
Keep the model the same, keep the task the same, but feed it different data sets.
Ah, okay. And see if the results stay consistent.
Exactly. If performance jumps around a lot depending on which data set you use, it might mean the model learned something weird about one specific data set, not a general pattern.
Right. Sensitive to the training data specifics. If it's great on one set but bad on another, even if they're meant to be similar, that's a red flag. Data dependency.
Okay, so that's reproducibility. The second one is diversity.
And this one checks for model bias.
Looks like it. Here, they keep the data set the same, keep the task the same, but swap out the AI model itself.
Okay. Same data, different models. Why?
Well, if different types of models act very differently on the same data, it could mean certain designs are just inherently better for that task.
Or that some model types might have their own built-in biases in how they process things.
Exactly.
That's also super critical. Different architectures like the CNNs and transformers they used, which we should get into.
Yeah, we will.
They process info differently. So testing a variety tells you which type works best for this problem, and maybe if some types just aren't a good fit.
All right, let's dive into the specifics for AI model set A. For reproducibility, they used 3 data sets, just called A, B, and C.
Okay. Simple enough.
Across all 3, the number of labels was that initial 29, consistent with the first version Model A.
Right. 29 classes.
What changed was the average samples per label and the total samples. Dataset A had like 70 samples per label, about 2,000 total. Dataset C had way more, 134 average samples per label, almost 3,900 total.
Okay. Quite a range in size and maybe balance.
Yeah.
That variation is key for checking generalization, like you said.
Yeah. A model that does well across all those different data distributions is likely more reliable.
Less likely to be thrown off by the specifics of just one data set. Makes sense.
Then, for diversity in set A, they looked at 3 different AI models.
Okay. The different architectures.
Yep, EfficientNet B1, that's a CNN, convolutional neural network.
Standard for images, yeah.
Then VITB16, a transformer model.
Vision transformer, okay. taking ideas from language processing.
And Swin-based patch 4, Windows 7 2.24, a hierarchical transformer.
Trying to blend the best of both worlds, maybe?
Seems like it. And their table gives a great snapshot. You see differences in input size, number of parameters gives you a feel for complexity.
Right, how big the model is.
And computational cost, the FLOPs.
How much number crunching it needs.
They also highlight key features. EfficientNet uses these special blocks designed for scaling efficiently.
Uh-huh.
VIT chops the image into 16 by 16 chunks or patches and uses global attention.
Looks at the whole image at once, basically.
And Swin uses smaller 4 by 4 patches but focuses attention within local windows first.
More localized processing initially. Interesting comparison of philosophies.
Definitely.
CNNs like EfficientNet have been image workhorses, great at hierarchical patterns. Transformers like VIT treat image patches like words in a sentence surprisingly effective.
Yeah.
And hierarchical ones like Swin try to mix local and global attention maybe more efficiently.
And the table mentions strengths and weaknesses too, like EfficientNet is fast, but might struggle with really complex patterns.
Okay.
VIT is good for complex images, but needs more compute power.
Right. That really shows why testing this diversity is so important. No single perfect model.
Exactly. Okay, moving on to AI model set B. This is where they level up. Increase the classes to 47.
Ah, the bigger set. 47 classes now.
So for reproducibility testing here, 3 new data sets, A, B, C again, but now consistently with 47 labels.
Okay.
And generally, the average samples per label and total samples have gone up compared to set A.
Mm-hmm.
More data for these extra categories.
Right. So a richer, more challenging learning environment, more categories, more data per category, finer distinctions needed.
But also maybe more risk of overfitting if you're not careful.
True. Definitely more complex.
And for diversity in set B, again, 3 models. And these are kind of like upgraded versions from set A or different configs.
Okay, what are they?
EfficientNet B2, so bigger CNN.
B1 to B2. Makes sense.
VIP B32, now using 32 by 32 patches instead of 16 by 16.
Oh, bigger patches for the transformer. Interesting change.
And Swin large patch for Windows 7 224, so the large version instead of base.
Base to large. Okay, so generally bigger, more powerful versions across the board.
Yeah, looking at the attributes, parameters generally went up for EfficientNet and Swin. Compute costs also generally up, which you expect.
More capacity, more computation, standard trade-off usually. The VIT patch size change is notable, though.
We get to that compute surprise in a sec. But yeah, it's insightful seeing this progression, B1 to B2, base to large, increasing model capacity.
Right, and that VIT change from 16 by 16 to 32 by 32 patches. That's significant. It changes how the model first sees the image.
How so?
Bigger patches mean it starts with a coarser, lower resolution view. Might struggle with tiny details, but could be better at seeing the bigger picture, the broader patterns.
Okay, now let's compare set A and set B directly. First, the data sets.
Okay.
For types A, B, and C, you clearly see that jump. 29 labels in set A, 47 in set B.
Yep, clear increase in classes.
And like we said, average samples per label and total samples generally went up too. More data across more categories.
Really emphasizes that deliberate step up in complexity for set B models need to learn more nuance.
Right. Now, the AI models themselves, the upgrade path was pretty clear. EfficientNet B1 to B2, VIT B16 to B32 with that patch change,
Right.
and Swin-based to large.
Got it. Straightforward upgrades.
Input size. Only change for EfficientNet went up slightly from 240 by 240 to 260 by 260.
Okay, maybe let's see a slightly finer detail.
VIT and Swin stayed at 224 by 224 input.
Interesting. So for VIT, the input size didn't change, just how it was broken down into patches. They were specifically testing that granularity effect.
Seems like it.
Hmm.
Now, parameters, the complexity measure. Increased for EfficientNet B2 and Swin large. Makes sense, bigger models.
Yep, more trainable weights.
But VIT's parameter count stayed the same, even with a patch size change from 16 to 32.
Whoa, okay. That is interesting. So the models over on capacity didn't change, just how it initially processes the image.
What does that imply?
Well, it suggests the patch size change probably affects the model's inductive biases, its built-in assumptions about the data, how it attends to things, but doesn't make it a fundamentally bigger model in terms of learnable stuff.
Okay, subtle but important difference.
Definitely.
And finally, compute. FLOPs. For EfficientNet and Swin, compute costs went up in the bigger B2 and large versions, as expected.
Right, bigger models, more calculations.
But here's the kicker. For VIT, the compute went down. significantly.
With the bigger patches.
Yeah, from 17.6 billion FLOPs for the B16 version down to just 4.4 billion for the B32 version.
Wow, that's a huge drop, almost 4 times less compute.
Exactly.
That's a key insight right there. We often assume bigger, better models always need more resources, but this shows architectural choices like V by T's patch size can lead to massive efficiency gains.
Yeah,
Trading maybe a slightly less detailed initial view for way less compute, that could be huge for deployment, especially where resources are tight.
absolutely. So wrapping this up, what we've really dug into here is this iterative process Coup Research used.
Yeah, honing the AI.
It really hinges on understanding that balance, that trade-off between recall and precision. Model A, the wide net. Model B, the precision follow-up idea.
And the importance of proper evaluation, reproducibility for data bias, diversity for model bias, not just looking at one number.
Right. Testing across different data sets and different model types. And that progression from set A to set B in more classes, upgraded models, shows that push towards more sophisticated, hopefully more accurate AI.
And it all comes back to that first problem, right? Telling defined known data apart from new undefined stuff, like known spam versus a brand new attack.
Yeah.
Their two-stage approach, high recall and high precision, seems like a pretty smart way to tackle it. Understanding these strengths, weaknesses, the impact of classes, patch size, it lets researchers make better choices.
So you've now seen just how deep this rabbit hole of AI testing and refinement really goes. It's
Okay.
pretty complex stuff.
Definitely is.
Thinking about those different strengths and weaknesses we saw, the CNNs, transformers, hierarchical transformers, what are the potential implications, you think, for where AI development might head beyond just STAM filtering?
That's a great question to leave people with.
Yeah. Like, how might these architectural choices impact performance or resource needs, or even what tasks they're best suited for? Medical images, self-driving cars, creative AI.
It's huge. Those trade-offs we saw, compute cost versus detail, local versus global context, the inherent biases of architectures, they will shape the future of AI. Understanding these fundamentals is key.
Not just for building better AI, but deploying it thoughtfully, too.
Exactly. Responsibly, across all sorts of applications.
Absolutely. Well, thanks for taking this deep dive with us into Coup Research's performance review. It's been really fascinating seeing the detail and strategic thinking involved.
Yeah, good stuff.
Until our next deep dive, keep those curious minds working.